Welcome to Reconstructing Relativity. This is the second video in the series in which we explore the idea of a constructive model. What a constructive model is, why Einstein didn't present one for special relativity, and what he did instead. Eventually, this is going to be the core of my presentation, the presentation of a constructive model. So you might ask, why is it called reconstructing? What's the deal with the constructive model? Einstein based his special relativity on a formal principle. He didn't present a constructive model, and I'm going to attempt to present one in this video series. So what is a constructive model? A constructive model is a visualizable explanation for the physical phenomenon. Because with the constructive model, we can see how it works in our mind's eye. And that's what's been missing in most relativity presentations. Now, let's delineate the difference between a constructive model and a formal principle. I'm going to show a couple of Einstein quotes, and you'll get a flavor of what the difference is. In 1919, Einstein said this was a decade after he developed his special relativity theory, but he said, when we say that we have succeeded in understanding a group of natural processes, we invariably mean that a constructive theory has been found which covers the processes in question. That sounds like a constructive model to me. But then later in his life, looking back and reflecting, he said, by and by I despaired of the possibility of discovering the true laws by means of constructive efforts based on known facts. The longer and more despairingly I tried, the more I came to the conviction that only the discovery of a universal formal principle could lead us to assured results. So these two quotes show that he wanted to present a constructive model, but you couldn't come up with one at the time, and he knew a formal principle would lead things forward. So what was his formal principle? Before we get into constructive model, well, his formal principle was this, that the speed of light in a vacuum is a universal constant. It will always be measured to be the same regardless of the motion of the observer. And this was a result that around the turn of the century, in 1900, were confirming that this was true. But it was difficult to understand how this could be true based on the understanding of wave motion at that time. It was a very surprising discovery and very difficult to reconcile. So to understand why this was surprising, let's first look at sound waves, acoustic waves, okay? So these behave in a way that we expect. We can measure the speed of a sound wave with two detectors, each with a clock to record when the sound wave arrived. And so we set up a couple detectors a known distance apart, and the speed is distance over the time difference. Also, consider for a moment the familiar, intuitive, also called Galilean notion of relative motion. Common sense relative speeds are found by simple subtraction. Imagine you're in a car going 75 miles an hour and you pass a truck that's going 65 miles an hour. You pass the truck at a rate of 10 miles an hour. That's your relative speed. It's simple subtraction. So 75 minus 65 equals 10. That's the way we expected things to work, and most of the time that's how it works for objects that are going slow. But if we apply this simple notion of relative motion to acoustic waves, what do we see? What happens? If we have our sound detectors set up sitting still in our backyard and we measure the speed of a passing sound wave, we'll measure about 760 miles per hour for the speed of that sound. But if we strap our detector setup on the back of an airplane, and we measure the speed of sound as we're flying away from the sound wave will pass us more slowly. It has to, chase us and pass us. The sound wave's chasing us, so it passes us more slowly than if we were sitting still. And again, we can add these up. If our plane's going 200 miles an hour and the sound wave on the ground is going, 760 miles an hour through the air, then with our detector on the airplane, we'll measure it passing us at only 560 miles an hour, relative speed. But if we turn the plane around and fly towards the oncoming sound wave, the wave will pass us more quickly. We'll measure the speed of sound relative to our plane as being 960 miles an hour. And again, these things add up in a very simple way. 760 plus 200, 960 relative speed. So having this understanding of relative speeds and how it works with sound waves, you might now ask, well, what's the problem? Well, the problem is that when it comes to light waves, it doesn't work that way at all. And it's pretty shocking when you realize that ain't how it works for light. Sound is a wave that travels through the medium of air, and it was assumed that light is a wave that travels through the medium of space. There's no air required to make light pass. But why wouldn't they work the same way? And big mystery. That's a good question. And that's what I wanted to understand. Because if you start with the formal principle, you'll be left confused by the counterintuitive results of relativity. But a good constructive model can straighten these things out. So, again, Einstein's formal principle is the speed of light is always measured to be the same, but how is that possible? This is the puzzle that Einstein couldn't resolve. He couldn't see it in his mind's eye, but he knew the principle was true because experiments showed that it was true. So let's apply this to an example of a light wave. Suppose a supernova exploded and a flash of light from it swept across our region of the galaxy. And as it passed Earth, we also had a rocket which was passing Earth at an extremely high rate of speed, almost the speed of light. Well, the formal principle says that of relativity says that the measure on Earth and the measure in the rocket ship would measure the same speed of light regardless of how fast the spaceship was going relative to Earth. No matter what your speed or your direction, always measure the same speed of light. And that seems crazy, right? But it's true. The formal principle is true. But it will take a constructive model to understand why it's true and how that works physically. What did Einstein do with his principle of relativity? Well, he did a brilliant thing. He did the math. He essentially said, forget about the concept of wave traveling through the medium of space. We don't need to figure that out to do the math. We can rely on the formal principle. And he was right. But importantly, we're still rather confused as to how relativity works physically because there was never a constructive model that explained it. Now, there's a few things that I'd like to make clear before, we get farther into this. You might be thinking, who is this guy and why does he think he can do what Einstein never did, create a constructive model? Well, first of all, there's good reasons that why Einstein couldn't create a constructive model at the time. Remember, he did this in 1905. And at that point, there were, still a lot to be learned about physics. And so I have the benefit of not only Einstein's results and the verification of special relativity, but everything that's come since then as added information. So there's Einstein was absolutely right. The formal principle that he used is absolutely correct, and all his results are correct. What my constructive model, the only thing it can do is clarify what's going on physically. And so in a way, I think my constructive model will serve as a prequel to Einstein. It'll show why the formal principle is true, and it'll help explain some of the other phenomena in a more clear way so that things aren't as confusing, as mystifying. And that's the goal. as far as who am I to do this, I mean, I may get into that a little further about what my background is, but it's not really important. What's important is that Einstein did it the way he did it because that's all he could do at the time, and he was brilliant to do it that way. And I think that even though other people have had access to the same information that I have, certainly, there's probably a great reluctance to, in quotes, air quotes, go against Einstein in any way. And but I want to make it clear, I'm not going against Einstein. I'm certainly not saying he was wrong in any way. I'm just trying to, my goal was to understand what was going on, and to the extent that that was my goal, I satisfied myself that with the constructive model we can understand it better, and that's what I want to share with you all. So understand that people who studied physics and are physicists may reject this notion because they're already fully ingrained in Einstein's approach and his technique, and they've already accepted that, and they don't probably feel that they need anything else. But for people like me who just want to understand a little better, hopefully this modeling that I do will be helpful. It certainly achieved the goal that I wanted to achieve, which was to understand what's going on physically better. So what will we be looking at in this series? Many of Einstein's special relativity results, including time dilation, length contraction, and the twin paradox. Again, they're all true. They're all proven to be true. We're just going to try and understand it more clearly. Einstein brilliantly saw that to make it work mathematically, he had to drop the idea that things like length and time were universal. Length and time became relative quantities, which was a huge breakthrough in physics, and leads to some philosophical questions, which we'll get to eventually. What does my constructive model look like? I will get to that in the videos that follow. Also, I wrote a book that develops the model step by step, and it's available on Amazon. Yes, there's the title, and I'll get to that part about truth eventually. Thanks for watching. Please consider liking, subscribing, and clicking the notification bell so you'll be alerted when my next video is uploaded. Periodically I'll drop little bits of music in that were either inspirational or some way go on with the theme of this project. So enjoy this one.